Hi friends, today's topic is capacitors and of course capacitance also. Now what is a capacitor? It is nothing but a system of two conductors separated by some insulating material. Of course, in some special cases, even a single conductor is considered to be a capacitor. There we assume that the other conductor is placed at infinity. Now, capacitor is an important element in many circuits. It is used to store charges. There is something called as capacitance of a capacitor. It is denoted by C. It's nothing but the charge divided by the potential difference by which the plates are separated. The unit is farad. I mean, 1 farad is nothing but coulomb per volt. Now, this is the symbol of a capacitor. This is the symbol of a capacitor with fixed capacitance, and this is the symbol of a capacitor with variable capacitance. Let's move forward. Dielectric strength. There is nothing to explain here. I'll just read the definition for you. The dielectric strength is nothing but the maximum electric field that a medium can withstand without breaking down of its insulating property. The dielectric strength of air is about 3 into 10 power 6, and the units are same as electric field, volt per meter. Now, there are different types of capacitors, like you have parallel plate capacitor, you have cylindrical capacitor, you also have spherical capacitors. I'll start with the I'll start with the simplest capacitor, that is parallel plate capacitor. Say these are your two plates separated by some distance d, and there are some negative charges accumulated on this plate, and there are some positive charges accumulated on this plate. If q is the charge on each plate, of course here it will be minus q, then the surface charge density here will be sigma is equal to q by a, assuming the area of each plate is a. Then here it will be minus sigma, of course. Now here you have three regions. The first region is to the left of the first plate, second region is in between the two plates, and the third is here. Now I want to calculate the electric field in these three regions. Note that here we are assuming the d to be very small compared to the area. D square is very less than a. So because this d is very less than a, and I want to calculate the electric field just near the plates, so I can take them to be infinite plates. So because my distance is very less when compared to the area, so my formula becomes electric field in the third region is sigma by 2 epsilon towards the right direction, and this is due to the positive charge plate, and there is another this thing minus sigma by 2 epsilon naught. These are due to the negative charges. This will be towards the left, this term will be towards the right, and this will be towards the left, so they both get cancelled, and finally you get 0 in the third region. This is in the third region. Similarly, in the first region also you get the electric field to be 0, and in the middle the electric field due to the positive charges will be in this direction, and due to the negative charges will also be in this direction, because you know that electric field lines go out of positive charges and into the negative charges. So here they don't get cancelled, instead they add up, and the magnitude is this is sigma by 2 epsilon naught, and this is also sigma by 2 epsilon naught due to both these things. Hence the net electric field inside becomes sigma by epsilon naught. So this is the electric field inside this or in the region between these two plates, and the direction, as you know, is from positive to negative. Please note that this is not true everywhere. The field lines are not this way throughout this region. Towards the end what happens is they bend in this way just near the edges. This effect is known as fringing of the field lines. This happens because the surface charge density and henceforth the electric field are not strictly uniform on this entire plate. They vary, but we have this assumption, right? D square is very less than a. When we take this assumption into consideration, we can ignore these effects, and hence say that E is equal to sigma by epsilon naught inside this region. Here, if I write sigma as Q by A, where Q is the net charge on one plate and A is the area of the plate, my E becomes Q by A into epsilon. Now, pay attention. You know that the potential difference can be written as the electric field into the distance by which they are separated, assuming the electric field to be constant in this region. Now, I know that E is Q by epsilon naught into A. So, this will be my potential difference. If I send this term V to the right side and all the remaining terms except Q to the left side, I can write Q by V is equal to A epsilon naught by D. Now I know that Q by V is nothing but my capacitance from the first slide. So my capacitance here becomes A epsilon naught by D for a parallel plate capacitor. As expected, it is dependent only on the geometry because epsilon naught is a constant. It is some 8.85 into 10 power minus 12 coulomb square per Newton per meter square, of course. And A is the area and D is the distance by which they are separated. So capacitance basically depends only on the geometry of these materials. Take an example. If I make a parallel plate capacitor whose plates are having area of 1 meter square and if they are separated by a very small distance of 1 millimeter, and if I put these values in this formula, I get my capacitance to be some 8.85 into 10 power minus 9 farad, which is very small. I mean to say that 1 farad is a very big unit. So we are going to deal with values as small as this. So the common units are we have 1 microfarad, which is nothing but 10 power minus 6 farad, and we have 1 nanofarad, which is 10 power minus 9 farad, and you also have 1 picofarad. This is 10 power minus 12 farad. Okay, let's move forward. I have a capacitor here, and unlike before, I have something in between them. I filled the space with a dielectric material. I explained you what is a dielectric in the last video. Now definitely the capacitance is going to change. How does it change? Before you knew that the capacitance was A epsilon naught by D because before the medium was air or vacuum. Hence you used epsilon naught here. Since now the medium is different, you just have to use another epsilon, where the epsilon is the permittivity of the material placed in between these two plates. So this gives you the new capacitance. Well, everything is fine, but now the question is how to calculate the new epsilon. Before saying that, I should tell you something called as dielectric constant. It is denoted by K, and it is a characteristic of material. I should say that the new epsilon is nothing but K times the permittivity of free space. As you see that K is nothing but epsilon by epsilon naught. It is a dimensionless ratio. And note one more thing, K is always greater than 1. This is the golden point. I mean to say that the permittivity of any medium will be greater than the permittivity of free space. The free space is something which has the least permittivity. So here you know that capacitance is proportional to the epsilon in parallel plate capacitor. Hence you can also write K as the new capacitance by old capacitance. So in other terms, I'll write it as C is equal to K C naught, where C naught is the old capacitance and C is the capacitance when dielectric is placed. This result holds for any capacitor, although I proved it for parallel plate capacitor. This holds for any other capacitor also. But the condition is the dielectric should be inserted fully, as shown in the previous slide. Now, what if the dielectric is not placed fully? If some partial, if it is placed partially or something like that, you will understand how to do that, how to deal that situation after the next problem. A slab of material of dielectric constant K has the same area as plates of parallel plate capacitor, but has thickness 3 by 4 D, where D is the distance by which these plates are separated. Now, I have to find the new capacitance. See, I know that the potential difference can be written as electric field into the distance by which they are separated, assuming the electric field to be constant. Now, if E naught was my electric field before this dielectric was placed, this was the potential difference before. So now what I'll do, I want to calculate the potential difference first in this place across these 2 points. It will be epsilon naught. There the electric field did not change, right? So the distance is d by 4, and the potential difference between these two points will be, here the electric field has changed now. By what amount? See, you know that capacitance is q by v. I can write it as q by e into d. Since charge and distance are constant, I can say that capacitance is inversely proportional to the electric field. So by placing a dielectric, if my capacitance gets multiplied by a factor k, then my electric field gets divided by k. Got it right? So my new electric field in this region will be epsilon naught, E naught by k, and the distance here is 3d by 4. So this gives my potential difference between the two plates. If I take a E naught into d common, inside brackets I'll get 1 by 4 plus 3 by 4k. Now, as you know, E naught into d is V, where E naught into d is V, where V is the potential difference before the dielectric was placed. So as you see, the potential difference has got decreased. Why am I saying it is decreased? Because as you know, 1 by 4 plus 3 by 4, 1 by 4 plus 3 by 4 is 1. But here it is not 3 by 4 now, it is 3 by 4k. And you know that k is always greater than 1. So 1 by 4 plus 3 by 4k is less than 1. Hence the potential between these two plates has got decreased. Hope everything is clear till now. Let me write it this way. Let the old potential difference be V naught, and let this be the new potential difference. Hence, I know that the capacitance is charge divided by potential difference, right? So the new capacitance will be, the charge will be the same, but the new potential difference is nothing but this one, V naught into 1 by 4 plus 3 by 4k. And simplify it, you will get this thing as q by V naught is capacitance of, old capacitance C naught, and this will be nothing but 4k by k plus 3. As expected, capacitance has been increased. That's it. Now you know how to calculate the capacitance when dielectric is placed in between these two plates. And in the next video, I'll tell how to calculate the effective capacitance when you have some combination of capacitors, and also how to calculate the energy stored inside a capacitor. That's it for today. Keep watching. Bye.